Thanks everyone for inviting me here. It's good to be back. I come from the storage industry. I work for Western Digital, and I wanted to tell you today all about these awesome new memories, resistive memories, that we believe in our research group have a good, fair chance of displacing a large fraction of DRAM and perhaps even some NAND flash in the next 10 years or so. So by way of, I'll tell you today a little bit about the memories, but mostly about how I think the RISC-V should connect to them. And I need to make a couple of general comments by way of introduction. The first one is I'll tell you some personal opinions that are not widely shared, right? So caveat emptor. And the second is that this is really targeted toward those of you who are seeking to displace some of the gorilla from the data center, right? So if you're interested in little embedded cores, this is probably not the talk for you, and you should ignore most of what I'm saying because the rules are different if you're working in a mobile world or an embedded world. So I am part of this research group at Western Digital in San Jose, and there's a lot of folks who contribute to this presentation. It's only a small fraction of the data I'll be showing you is mine, so I want to thank them first. Too many to single out. So what are these new resistive memories? You've all heard about the 3D crosspoint and so on. There are two general pieces or general categories of physics that we talk about when we talk about the resistive non-volatile memories. The first category we call a ReRAM or resistive RAM, and there is more than one kind of physics that we talk about here, but normally I'd show you electron micrographs, but because secrecy I can't really show you any new stuff, so I just picked out these a couple of well-rehearsed review papers from about 7 years ago. So this is one kind of ReRAM where you take a little piece of insulator, you sandwich it between two metal electrodes, and then the first thing you do is you zap it with a high voltage, right? So you do this electrical breakdown. And if you're smart about choosing your materials, this breakdown will create a filament that becomes conductive then. And by passing current one way or another, you can move atoms through the narrow portion of this filament, and you can change its resistivity that way. And you use this as the basis of storing bits, right? The other mechanism that's actually a bit older, if I understand well, that was discovered by a self-taught garage thinker in 1968, is called phase change memory. And the idea is here is to use this material called the chalcogenide. These are very interesting materials. They are amorphous semiconductors. They have two solid phases, so you can melt them and then cool them one way or another. And they congeal into two different phases. They have different resistivities. So then you again read it out with a resistive readout with an electrical pulse, right? So what's nice about these two memories is that because the readout is resistive, it's a lot faster than NAND flash, right? And it's non-volatile. These are non-volatile mechanisms. These have been around for a while. The chalcogenides are actually deployed in DVDRs for at least, 15 years now. That's the purple stuff on the back of a DVDR disc, right? Now, if you put them on a chip, you get this big advantage. You get the latency that's much higher than the currently dominant NAND flash non-resistive electronic memory. So these latencies fall kind of in between. This is the scale in seconds of latency, and I was a little bit careful of drawing. These are rough diagrams, right? But I was careful of to choose the left edge of these rectangles a little precisely. So, for instance, if you go onto Newegg and you buy the most expensive DRAM for your gamer PC, you can overclock it up to wazoo, but there's one thing that doesn't really change much, which is the TRCD, which is the latency from the time you latch in your address bits to the time the data bits start coming back, and that's about 9 nanoseconds today with DRAM. This is a fairly stringent physical limit. You can get it a little bit faster, but not much if you want to make it dense, right, and cheap. In contrast, on the other end, we have a NAND flash, which is dominant in our solid-state drives today, and that is sitting around 50 microseconds here. And this is not actually a very hard physical limit, but again, it's the economic pressures that make it so. And by the time you're done with it, you end up at about 100 microseconds latency to get your bits back, right? So then in between, there's this huge gap, and this is, we see that as the main inroads for these new memories. So phase change starts around 80 nanoseconds, and resistive RAM, we believe, around 200, depends on the technology. And so then the question is, you look at this graph from a distance, and you ask yourself, well, where does this attach to the existing computing architectures? What do we sell as a storage device to you? So you could go left, right? You could treat it as the main memory, or you could go right and treat it as a storage. The challenge in going to the right is price, right? Because these are still fairly expensive compared to NAND flash, which is incredibly dense and cheap. The challenge on the left is that the DRAM infrastructure that's kind of evolved with DRAM over the last 30 years or so is not quite a good fit for all this for these new memories. So we're a hands-on research group, and we actually built both, right? We built both an NVDIMM, this is circa 2012, an NVDIMM with storage class memory, and then we built a bunch of these PCI Express cards that are just like PCI SSDs. And I can tell you with some confidence that this just plain doesn't work, right? Because in 2012 when we built it, there was no computer that you could buy off the shelf that you could plug in an NVDIMM into and it would work. And this is, of course, not not any kind of physical limit. This is just the way the architecture is today, and there are major economic forces keeping it this way. So there is a lot of talk about changing the architecture of CPUs to accommodate these new memories, to increase the latencies, introduce stochastic latencies, and so on. But I'm going to argue today that you shouldn't do this, right? There's a better way, I think. The other way, the PCI Express cards, this for sure does work. We've made a bunch of them. We tried different protocols. We invented some protocols and patented them. But the general reaction is meh, right? Because you start with a memory that is 80 nanoseconds, and then PCI adds a microsecond. So you throw away most of your value right out the door. Right? So I think there's a better way. And before I explain what I think that better way is, I mean, you could tell from the title, right? It's a coherent attach. Let's kind of go back to the days of my youth, what the enterprise systems used to look like in 1990s or so. So there was one core, right? Remember those days? And the core back in the day had something called a front-side bus. And this was sort of a privileged bus where we had a chipset. So these two chips, the South Bridge and the North Bridge, would attach to it, and they would talk this privileged protocol. So it was, king of the hill and one road leading into the village, and then the gatekeepers to the villagers. So the North Bridge, the function used to be the memory controller, right? It would control what the DRAM used to be. Now, this wasn't just DRAM. There was other kinds of memory, but DRAM kind of prevailed and won. So the thing to keep in mind here is that this memory controller is actually outside the CPU die. This is not the way it is today. And then on the South Bridge, we control the peripherals. Today, it's PCI Express, but it used to be PCI. Before that, it was ISA and EISA and so on. And there was a host bus adapter for the storage. And we had either SCSI or ATA drives, right? So over the next 10 years, a couple of very interesting things happened. One is that the memory controller kind of got sucked into the CPU die. And the reason being that some shrewd folks figured out that all these DRAM started to look kind of the same, right? This diversity of memory has narrowed down to one type of DRAM that was, there are different latencies and so on, but it all kind of talks roughly the same protocol. And this allows more control to the CPU maker of the market, right? Obviously, that's why 99.3% of the market today roughly looks exactly like this, and there's one dominant player. The other thing that happened is that folks realized that this lithography advances are starting to slow down, right? So Moore's law is coming to an end, as we know. And then there was an idea, so why don't we meet the marketing requirements by saving money on dicing these wafers, and we just leave multiple CPUs in one die. We call it symmetric multiprocessing nowadays, and the problem here is that, of course, the lazy programmer doesn't want to bother with sending messages and ensuring coherence of their programs running on different cores, but rather we have hardware-accelerated coherence protocol that keeps track of these caches and makes sure they're all seeing the same picture of the main memory, right? So this is what you want to displace, right? This is the big market. This is the big money that you want to get into with your CPUs. So on the peripheral side, we have a similar situation, except now it's PCI Express, and we still have the HBA, and we have the SAS and SATA attached disk drives mostly, and then some SSD. A little bit of the market is SSDs. Of course, the SSD, we look at the second derivatives. It's speeding up, but it's still a minor fraction of the market. Right? Okay, so these are the two options we tried, right? To attach here and to attach here, and they don't quite do exactly what we want. So let's zoom in and try to understand why. So excuse my cartoons, this is very simplistic for those of you who are designing chips and memory controllers and so on. So for instance, on the memory controller side, what most folks think of as memory controller is this phi here, which talks to DDR protocol like DDR3 or DDR4. And then there's a little bit of error correction. As here I drew H for Hamming. And then there's a logical protocol that actually understands these registers and talks to the chips and sets them up and trains the lanes and so on. But the one thing that's often overlooked, of course, is this CS, which I wrote here for coherent state. Right? So the coherence protocol here, the lowest point of coherence, the guy who hands out the cache lines and keeps track of where they are and who has them is actually the memory controller. Right? In the sense that, so normally people think of this as belonging to the coherence protocol, but that's not really true, because if you have multiple memory controllers, and most enterprise systems today do have, you have multiple sets of coherent states in different sockets on the motherboard and so on. So very conspicuously, the PCI Express, the peripheral attached, does not keep coherent state. There are some attempts to add this, like on Power 8 architecture with CAPI and so on, but they have their own challenges. So there's a completely different set of physical and logical layer. And then on the other side, inside the SSD, we have all this stuff that, again, most of you would like not to think about. There's the physical layer, that's fine. There's some protocol that we talk, but then there's this whole big mess that starts here. There's a translation layer, right? because these memories, they wear out, the NAND flash and also these new non-volatile memories. We have a wear leveling engine that moves data around all the time because otherwise you could kill it in a few seconds. There's usually an encryption engine because in a lot of enterprise settings you have to encrypt the data at rest because this disgruntled soon-to-be ex-employee can walk in and steal your data, right? And that DRAM doesn't do that. And then you have a much beefier error correction engine, right? So now enter these new memories, and the tendency is to take all this functionality here and to shove it right here into the memory controller, and then you end up with this Godzilla memory controller here. And I say don't do this, right? There's many good reasons why you shouldn't do this in this community. One of them is that we already own a lot of essential IP that you need to run these kinds of flaky memories. The second one is that I don't think this makes any sense for you because you'd be wasting, say, 10 square millimeters of silicon on memories that don't exist yet. They're not proven. We don't know which particular technology is going to win. So in 10 years, we can revisit this. You can suck in this memory controller back into the CPU die, but I think for now you should pull it out. And in particular, I think you should pull it out in a coherent fashion, right? So what you should do is you should open a big fat coherence port straight in the heart of your coherence fabric, right? And let us attach with some phi. We can discuss what's the optimal way to do this phi, but then let us keep the coherence state on the peripheral, right? This is the key. We have to be the lowest point of coherence. And then we'll do all this nasty stuff that is bread and butter for storage guys, but the DRAM guys and the memory guys don't really think about it. So this is the point of my talk. If you believe me, you can take a break and get coffee. If you don't believe me, I'll try to explain first why do I have this strong opinion, and then how we might do this. I don't actually know the answer to the second question, but the why I can talk about for an hour or so. Yeah. So the first, well, the thorniest problem, right? It's not the only problem. Is basically these new non-volatile memories, just like NAND flash, they're really bad memories, right? You send some data to it, and it comes back all messed up. So the error rates are not quite as terrible as with NAND flash, but they are pretty bad compared to DRAM, just to put things in perspective, right? With DRAM, if you buy a DIMM stick from a store, it's gone through quality assurance. The error rate on DRAM is 0. It's exactly 0, not 10 to the minus 15. We just happen to live in a radiation-full environment, right? So occasionally you get a cosmic ray that discharges a capacitor, and then the error rates go up to, say, 10 to the minus 11-ish, 15-ish or so. So the new non-volatile memories like resistive RAM are nowhere near that kind of performance, right? They're, say, 1 in a million bits comes back wrong. So you could construct a Hamming code like with DRAM to take care of that, but then your code would be, code rate would be like 0.5, so the profits go out the window, so that's not even considered. LDPC is the kind of sledgehammer of error correction for NAND flash. We don't generally think that this is needed. The error rates are not quite as bad. So you end up with BCH. Now, BCH error correction has this nice property that it's a Galois field, right? So you can calculate something called a syndrome check. So there's this quick calculation you can do to find out if there are any errors in your code word and how many there are. So how far you are from the node in Galois field. And this is this plateau here. So what I'm showing here is, again, I'm sorry I had to remove the numbers because secrecy and patents and whatnot, but on the y-axis is the latency. And then here along this axis is if you pick a code word, say a cache line, so 1,000 bytes or 512 bytes, there's a decreasing fraction of packets that have a certain latency to correct it with a particular choice of BCH algorithm, right? So you see this plateau here is that, say, 99.9% of all your packets coming back will have no errors, and those you can process really fast. So you can treat it as main memory. Right? Now, 1 out of 1,000 times or 1 out of 10,000 times you run into a packet that actually has bits in error, and then you have to do much longer calculation to actually correct those errors. And you can't really do this fast and cheap, right? You can pick one. You can do it faster and then pay a lot more money, or you can do it like we do it normally on SSDs, and then it takes quite a long time. And what's worse is since these memories age, as they age, the bit error rate goes up, and then these latencies go up. And this latency here, the order of magnitude is roughly the same as a read, so you double up all the latency. So here you have a couple of choices, right? First is you can ignore this error correction, just send all the bad data to the CPU and let the CPU figure it out. We actually own 2 companies that tried to do this and fell on hard times, and the market seems to reject this solution promptly. So we think that this needs to happen on the device itself, and we send corrected data back to the host. If you send the corrected data, you can either slow down everything to this point here, in which case all your latencies go up by a factor of 2. We don't think that's a good idea. So of course, the best solution we think is to send you back stochastic latency packets out of order. Right? So this is something that DRAM doesn't do, but you guessed it, there is a protocol that was designed precisely for this kind of thing, which is a coherence protocol. Right? It's designed to handle out-of-order execution of CPUs and random timings of events. So this is the thorniest problem, right? But it's not the worst case. The worst things actually come from these macroscopic effects and from the asymmetry in how you write and read to these memories. Because all the physics that we've seen so far for non-volatile memories have a very asymmetric latency for writes and reads. So if you have writes and reads coming in combined, then you'll occasionally have spikes on latency on reads that are caused by writes, right? Because of the way you block the data. And then for some kinds of memories, for instance, with phase change, you're heating the substrate to 600 degrees centigrade. So the volume is very small, so heat is not much. But if you keep doing this at 50 gigabytes a second, then of course the whole thing overheats. You have to stop for milliseconds to cool it off. Right? So again, this is not really the kinds of problems that you deal with DRAM. So we don't think that that's best done in a CPU, at least not at this point in history. So we think that we should get rid of this deterministic latency of DRAM and just move all these decisions out of the die and use the coherence protocol to synchronize all. The second set of problems comes with this aging, right? So the aging is problematic, right? So the number of writes you have to any of these new technologies may be, say, in a million to 10 million range. And what that means is that if you're on a peripheral device, you already have these big blocks, so it takes a while to kill it if you don't have any wear leveling. But if you use it as a main memory, as a DRAM replacement, then you can kill the DIMM in about 0.2 seconds. So you have to do some wear leveling, and moreover, it has to be really fast. So some years ago, there was this start gap scheme that I think was started by Professor Qureshi at Georgia Tech that was very popular in the academic literature. Unfortunately, the schemes are pretty fast. They have very low overhead, but they're also quite vulnerable to malicious execution, right? So we didn't really find any that are good enough that we put them in a product. And then there was a bunch of follow-up papers that tried to resolve these malicious kernel issues, but then they're vulnerable to denial of service problems and so on. So we have a bunch of our schemes that we patented that have this very nice feature that are really fast and they don't suffer from denial of service attacks, but they have the very high upfront cost of calculating the vectors that you put into these networks to do the translation of logical to physical addresses. And so you could then pre-compute these on, in MATLAB, right, in the lab, and then just load them onto your chip and then ship the device, and the controller ages with the device. And when the memory is done, the controller dies with it. So we think that's probably the most cost-effective way to do this. But now, this is really not something that CPUs do, right? If you have an enterprise CPUs, unless you're an Arduino, right, you don't really architect enterprise CPUs that age with anything and die after a while. Then again, we have the encryption issues, right? So DRAM doesn't really deal with encryption because if you pull it out, it loses all its data. But now, if your working set is in a non-volatile memory, then the power loss can actually be really bad, even if you try to encrypt on the fly, because the wear leveling can move your unencrypted data out from under you. So you can never be sure that your encrypted data is actually not accessible to folks outside, right? And then the pluggability and so on. So there's a number of these issues. So this is a bunch of answers to the question of why. I can keep talking about this, but I have limited time. So let's talk about how. So I can offer you two options for now. I don't know what's going to win in the market. But I think these two might be very interesting for the RISC-V community. So the first one is this very interesting idea of FPGAs and CPUs kind of merging into a single die. So a couple of things happened in the last 5 or 6 years is that Intel bought Altera, and Xilinx is now shipping these FPGAs that have a fairly beefy 5-core, 1.5 gigahertz ARM-A53 thing in them. So I got hold of one of these Zinc FPGAs. This is the first generation before UltraScale Plus, and they had a dual-core A9. And they also exposed this coherence accelerator port out. So I said, well, why don't we treat this fast new storage as just a coherent accelerator, except that it's not going to accelerate anything. It's just going to return what you give it, right? And then I wanted to see if I wrote the memory controller / storage controller in the FPGA fabric, how fast could that get, right? And the results, I think, are pretty interesting. So here's 1 microsecond latency, right? This is latency on the y-axis, and here's the block size on the x-axis. And again, we're trying to use this as main memory, so these block sizes of 64, 128 bytes are probably the most interesting for us. And you see that this region, these two curves are basically neck and neck, right, in latency. And the black curve here is that little Zinc board, and the red curve is our best idea of how to use PCI Express on Xeon, right? So you see that these latencies are comparable, but basically you're comparing a high-end Xeon with a Raspberry Pi, right? So this is great, right? If you guys make us an enterprise-grade, 8 cores RISC-V thing with the 50 gigabyte a second coherence bus, then this drops right down in a couple of 100 nanosecond range, which is exactly where we want to be for these new kinds of memories. So that's why I think this is the right way to connect. Now, just to make a comment, right, this red line is not a standard protocol. If you use a standard protocol, NVM Express, then you're right up here in the stratosphere with the block storage protocol. Right? So the second idea I have for you is what Mohammed just talked about, is to trust the fabric. Right? There was a famous computer scientist in the Bay Area who about 20 years ago said the network is the computer. Right? He wasn't wrong. He was just wildly premature in his estimate. So we love fabrics, right? We still sell storage, so all our storage is connected to some sort of Ethernet fabric. And we also love InfiniBand because we just showed off InfiniBand RDMA to phase change memory in about 2 microsecond latency or so. But if you think about it, all these are storage fabrics in the sense that if you're a lazy programmer, you have to still make a system call or you have to call a library function to fetch your data, then there's a local copy in your DRAM, and then you can operate on that data, right? What we really would love to do for the lazy programmer is we would love to have a fabric that you plug into and it shows up as memory, right? So you basically request cache lines from your fabric and the cache lines come back at a latency that's respectable. And so we are now turning our attention to Rapid I/O, which, as you know, is a very widely deployed chip interconnect fabric in the mobile world. And so the idea would be that then you would give us CPU or compute silicon that would attach directly to Rapid I/O through a coherence protocol, which the spec is out, I think, since April. Mohammed will correct me if I'm wrong. And then you can talk a 5-state, MoISC-like coherence protocol to the fabric, and we'll attach to the other side with storage, and you can attach DSPs and other compute engines. So that's pretty much what I've got. Here's the shopping list, right? So we don't make CPUs. We attach to whatever CPUs are out there. I think there's a huge market for RISC-V in the data center in many different guises. But I think to compete in this space, coherence was a dirty word in academia for about 10 years. I mean, this is absolutely necessary. You won't be able to sell anything that doesn't have hardware-accelerated coherence. I mean, message passing is fine for supercomputers and for scientific users, but not for Oracle database guys. This is a target that I sort of threw out there because that's roughly where competition is right now or thinking about being there. All the stuff that we've seen today is about an order of magnitude slower. You kind of need to be there to be competitive with IPC or speed, and this is the latencies that we see today. I think that the best way for these new memories to make inroads is for you to open as coherent ports instead of using this, trying to tweak DDR into accepting these weird memories. And either you could put some programmable logic on your RISC-Vs, which would actually come in very useful for other uses as well, right? There's a lot of other folks who would love to use these for accelerators, or to adopt a scalable fabric like Rapid I/O. And again, we can talk about why not Ethernet and why not InfiniBand, but there's issues with that, right? And I think this is a unique advantage of the RISC-V ecosystem over the competition because to make this work, right, to have a coherent port open up and be coherent, you kind of have to open up the innards of your coherent fabric to the guys who connect to it, and your competition is very reluctant to do this. So you could have a foot in the door there. I don't think it's a wise idea to try to make the non-volatile memory controller be part of the CPU yet, maybe in 10 years, maybe not even in 10 years. Because these technologies differ by enough that you cannot have one solution that fits all. Right? And then finally, I think you should get used to high variability main memory responses if these non-volatile memories take over the main memory. And so, hyperthreads, lots of them, yay. All right, so that's the end of my presentation, and I'm happy to take questions.
Great. Thank you, Dejan.
Well, you refer to the competing technologies, that's prevailing technologies
prevailing,
today,
yes.
Right? That's what you are probably meaning to say. And what kind of a response that you get from those people now? Can you introduce yourself? Oh, okay, I'm Shunpei Kawasaki from Software, Hardware, and Consulting LLC. Yeah.
So I guess the question is what kind of response? So I'm not sure I understand the question in the sense that there are very few coherence ports out there right now that we can attach to, right? This is the first one I could find. There's a second one now, but it's only pretty much Xilinx and ARM. Intel obviously has their own version, but it's not accessible to even us, right? Let alone. And then there's talk about new initiatives, but they're in very formative stages like CCIX and so on. So yeah, no comment. I mean, we could probably get down to the coherence latency of the coherence protocol itself between sockets on a motherboard if we could attach there. But with the prevailing technologies, we're not allowed to. With RISC-V, we'll measure it.
Okay.
And with rapid I/O, we kind of know, right? It's about 200 nanoseconds.
So you're advocating for the next generation architecture.
We sell storage, so whatever the next generation is, we'll try to sell for it.
So Dan, so I had a comment on I agree that you don't want to have the flash controller logic or the non-volatile memory control logic on the CPU chip, but I also think you do not want to have the coherence controller on the flash chip either. The way you can split them is just have a decoupled interface where you have tags on the memory transaction. It can be out of order, but I think the coherence is too tied to the processor side and too latency sensitive to be pushed off chip for any components. So I would just argue that maybe you'd want a slight modification to your partitioning, keep the non-volatile controller on the flash side or the non-volatile side, but keep the coherence and just have a decoupled interface between the two that's tagged and out of order. I think that would satisfy the needs.
Yeah, I'm in absolute agreement, and it goes back to my very first comment that my opinions are not widely shared. So it can be done both ways. I think that if you do it my way, then you can do the scale out as well. If you keep it close to the CPU, then you have to think about how to do scale out, right? Then you have to do some coarsening or whatever directory and scale out. This way you can scale out as much as the fabric will scale out, and you already have the fabric and you already have the RISC-V version with the interconnect to the fabric. Right, it's a question of trust, right? Do you trust the peripheral guys to be coherent with you? The latency is not an issue, right? The latency is just a question of power. How much power can you put on a wire and how big the wire is. But you can think of this as sitting on the same motherboard, in which case power is not an issue. It's the same exact power as in between sockets. It's just that you have to allow the storage guy to come into your kind of inner sanctum and prove the coherence, right? So yeah, it can be done both ways.
All right, very good. Thanks, Dejan.